We continue now with the final part of the lecture on computer architecture. In this part we discuss the CPU implementation. Okay, so let's revisit a little bit the C instructions, right? Because the CPU actually will be controlled by this instruction. The C instruction has C parts: what to compute, where to put the result, and the conditions for jump. Okay, and here we have the actual values for the three fields. The C bits defining on what operations we should do, together with the A bit that defines whether one of the input should come from the A register or from the memory. The destination bits, where we have 1 if given destination is active for destination A, destination D, and destination M. And finally the jump instructions that force the program to jump according to the instruction address given by the A register, again for given conditions. So let's see how the CPU will work. Okay, again we have the interfaces of the CPU. The CPU has inputs as the reset bit, a 16-bit instruction coming from the instruction memory, of course in machine language, and then data from the data memory. The outputs of the CPU are the program counter, which is can be incremented, can be set to 0, or can be changed according to jump instruction, and then information to write the memory. Write M will be whether memory has to be written or not. If write M is 1, then we need an address where to write in the memory and what should be the value we write to the memory. Let's see the CPU execute logic. It performs operations according to the instruction it receives. It can read or write the D and A register values, and it can read or write the memory according to the address given in the A register. Let's look at the fetch logic of the CPU, telling us what the next instruction is. In the instruction may include the jump directive, right? These are the last 3 bits in the word. As a result of the computation, the arithmetic unit will emit 2 control bits. Right, this will evaluate the condition of the jump. And then the next instruction is fetched according to the following. If the reset bit is 0, that is no reset, then if there is a jump, then the program counter has to be set to the value in the A register, otherwise the program counter is increased by 1. If reset is equal to 1, then the program counter is set to 0. Okay, let's have a quick look at the arithmetic unit. The arithmetic unit had 2 16 bits input for 2 operands, 6 control bits, 1 16-bit output, and 2 control bit outputs. We can see that this 6 input control bits nicely correspond to the bits in the C instruction for computation. Okay, C1, C2, C3, C4, etc., etc. Apart from bit A, that affects whether the input should come from the A register or from the memory addressed by the A register. Okay, and as we said, the output bits 0 and negative will help us to evaluate the jump condition. Okay, so let's see how the CPU should be then implemented. We have some help for this implementation, this chip diagram. The chip diagram includes the arithmetic unit, the D register, the A register, a program counter, some multiplexers for different data paths. It also shows data and address passes for connecting these units. What it doesn't show actually how to decode the instruction so that the CPU does actually what it is supposed to do. Okay, so this will be the CPU's control logic, and what we have help are these small circled C's. They show that here some control should be implemented. Okay, the same way this decode is not an actual chip. It just shows that here we have to implement some logic to actually demultiplex the control bits in the instruction. So the main challenge of the CPU implementation will be to connect these control bits in a correct way. Let's see two small decoding examples. Okay, for example, the A register, the implemented control will have to decide when to write to the A register and what to write there. Okay, so for example, here, if the control can see that this is an A instruction, then immediately we know that the rest of the instruction should be written to the A register. If the instruction is a C instruction, right, and this we can see from the most significant bit of the instruction, and in the C instruction the destination or one of the destinations is the A register, then the ALU output has to be written to the A register. See, and also in the figure we can see that there are two possible paths to the A register, either from the instruction or from the output of the arithmetic unit. Okay, another small example to see how to control the program counter. The program counter, of course, is increased if it is simply an A instruction. So let's see if it is a C instruction. Then our computer have to compare the jump bits of the instruction where the condition is given and the result of the calculation, that is the 0 and negative bits of the ALU, and from that figure out whether the condition is fulfilled or not. If the condition is fulfilled, then the program counter has to be loaded from the A register. Okay, and so on. Similarly, if you take any small part of this diagram, you can derive how to connect the control bits. Okay, so we provide a suggestion how to implement the CPU. Some of the components are given for us: the ALU, the A register, the D register, the program counter. And well, one possible code structure, this will be actually a rather long code. One possible structure is first to decode the instruction, whether it is A instruction or C instruction, and if it's a C instruction, then actually divide the bits that control the ALU, that set the destination, and that set the jump condition. Okay, then we could look at the control of the A register, the control of the D register, the control of the arithmetic unit, and finally deal with the flow control, that is evaluate the jump and set the program counter. To summarize this lecture, we discussed computer architectures in general and the hack computer in particular. We discussed what the stored program concept is, that is, even the program instructions are stored in the memory and can be manipulated just like data. We have seen that in our specific hack architecture we have a dedicated instruction memory, which is actually not the original von Neumann architecture, but an architecture that's called the Harvard architecture. The computer we built is a 16-bit architecture, including a ROM, a RAM, memory mapped screen, keyboard, 2 registers, A register, D register, and the program counter. And we know that we have to co-design the computer architecture and the machine language. So let's see how the course will go on. With this lecture and the related project, we have completed the hardware design of our computer. So in the rest of the course we will build the software hierarchy up to the high-level language and the operating system. As a first step of this software hierarchy, in the next lecture we discuss the assembler, that is the translator from assembly language to machine language. This ends the lecture on the computer architecture.